Welcome back to the Foundry by Forge College. So in our last explainer, we took a nice 30,000-foot view of the overarching architecture of Turbine. But today we're putting on our hard hats, rolling up our sleeves, and diving right into the actual engineer's blueprints for data delivery mechanisms in Turbine. We're going to figure out exactly how this data actually moves across the network without, breaking the laws of physics or our brains. Let's get into it.
Here is our game plan for today. 1. The data delivery challenge. 2. 4 core delivery primitives. 3. A concrete delivery scenario. 4. Plumbing and postal routing. And finally, 5. Tuning your delivery engine.
All right, starting us off with Section 1, the data delivery challenge.
Okay, so imagine this. You've got a massive 1 megabyte block of data, right? And as a network leader, you try to just naively broadcast that entire thing to every single node in the network at the exact same time. Well, it would be a disaster. It'd be kind of like trying to shout an entire novel to a massive stadium of people all at once. Your voice would completely give out, and the network connection would instantly choke. It creates this absolutely massive bandwidth bottleneck right at the leader's outbound connection. This core problem right here is exactly why Turbine needs specialized, highly tuned tools to keep Solana running lightning fast without completely clogging the pipes. Let's look at those tools in Section 2, 4 core delivery primitives.
Tool number 1 on our workbench is packet chunking. So instead of trying to heave that massive 1 megabyte block all at once, the leader slices it up into nice fixed size packets. Think of it like taking a giant, heavy textbook and mailing it out page by single page. This brilliant little trick means these packets can be transmitted independently and, crucially, in parallel across the network. It minimizes network fragmentation, keeps the packet header super small, and it makes buffering and retransmitting incredibly simple for intermediate nodes. Because honestly, they don't even need to know what's inside the full block to just forward their piece of it.
And that actually brings us to our second tool, which is the fanout tree. Rather than the leader exhausting itself trying to talk to everyone directly, Turbine organizes retransmit nodes into a branching delivery structure. Basically, the leader sends different subsets of packets to its direct children. Then, those children forward their specific subsets down to their own children, branching out exactly like a massive tree. This is a total game changer because it fundamentally reduces duplicate transmissions across network links and spreads the heavy lifting out, totally limiting that massive leader bottleneck we talked about earlier.
Now, tool number 3 is windowed retransmission. As all these packets are flying around the network, they're numbered in a specific sequence. Receivers use these sliding sequence windows to track exactly what they have and, more importantly, what they're missing. If a node suddenly realizes it missed a packet, it doesn't panic and ask for the whole block again. No way. It just sends a compact negative acknowledgement, or a NAK, asking only for that one specific missing packet. So the really beautiful part here is that this mechanism fixes microscopic gaps in the data stream without forcing the entire network into a costly full-scale redelivery.
Finally, we have an optional but incredibly powerful fourth tool, parity, or forward error correction. When you're dealing with a network path that's experiencing a lot of packet loss, constantly asking for retransmissions causes huge round-trip delays. So instead, the leader can preemptively send extra parity packets alongside the actual data. If a receiver drops a few packets, it can literally just use the parity data to magically reconstruct the missing pieces locally. It is an upfront bandwidth trade-off for sure. You send a little extra data right at the start, but it absolutely saves us from those crippling round-trip delays when things get rocky. So let's look at how this all comes together, kind of like an engineering spec sheet. We've got packet chunking trading a tiny bit of header overhead for amazing parallelism. Then the fanout tree trades some branching complexity to drastically reduce duplicate bandwidth. Windowed retransmission trades a little control traffic for highly efficient gap repairs. And parity trades some upfront byte transmission for massive latency savings. This exact combination of tools is what keeps the data flowing so smoothly.
Moving right along to Section 3, a concrete delivery scenario.
Let's actually run a quick simulation here with a 1 megabyte block and a branching factor of 4. Step 1, the leader packetizes the block into 1024 byte chunks and pushes a quarter of them to each of its 4 children, who then forward them down the line. Step 2, a validator down at the bottom is receiving the flow. But wait, it realizes it's missing packets 310 and 311. It immediately fires a quick knock upstream. The parent goes, yep, I have those right here in my buffer, and shoots them right back. It's literally like the post office losing just page 4 of your letter, and instead of making the sender mail the whole envelope again, they just fax you page 4. Step 3, for stubborn, lossy branches, the validator uses the parity packets from Step 1 to instantly rebuild missing data, 0 extra questions asked. By the way, seeing how simply these complex steps fit together is exactly why checking out the learning programs at Forge College makes understanding Web3 so accessible.
I really, really want to highlight this number right here, 0.25 megabytes. Remember, without our delivery tools, the leader has to push a full 1 megabyte to every single node. But because we set our fanout branching factor to 4, the leader is only pushing specific chunked ranges. Every single link from the leader to a child only carries a quarter of the total block. We just slash the leader's bandwidth requirement by 75%. That is massive efficiency in action.
All right, Section 4, Plumbing and Postal Routing.
To really wrap our heads around this, think of turbine delivery using two mental models, plumbing and postal routing. The plumbing metaphor handles bandwidth and throughput, so think of the network as a system of water pipes. The leader is your main reservoir, fan-out dictates how many smaller pipes we split that water into, and if we try to push way too much water at once, well, it backs up in queues. Postal routing, on the other hand, handles correctness and repair. Every single packet has a sequence address. If a piece of mail goes missing, we send a targeted request, a NAC, to the local post office rather than calling up the publisher and asking them to reprint the entire magazine. So plumbing gives us raw throughput, while postal routing gives us that rock-solid reliability.
Bringing it home with Section 5, tuning your delivery engine.
So if block delivery ever slows down on the network, here is your practical engineering checklist. First, measure. Look closely at the telemetry. What's the packet loss rate looking like? Are those NACs randomly spiking? Is the leader's outbound egress hitting a ceiling? Second, diagnose. If the leader is choking, well, your bottleneck is right at the top. But if NACs are heavily localized to just one subtree, you've got a bad branch on your hands. Third, tune. You can increase your fan-out to relieve the leader, boost up the parity for that bad branch, or tweak window sizes to prevent queuing. With this, you are now fully equipped to keep the system flowing smoothly. Now, if you write down just one single thing from this entire explainer, make it this quote right here. Selective repair beats blind retransmission. By combining packet chunking and windowed sequence tracking, Turbine pulls off these incredibly precise microscopic fixes without sacrificing an ounce of the blazing speed of its plumbing. It is just an incredibly elegant solution to a really tough problem. But of course, in Web3, the innovation literally never stops. As the network continues to scale up, we have to ask ourselves, how will these exact same delivery primitives evolve when we introduce complex data sharding? Well, that is exactly what we're going to tackle in our next explainer. To continue your Web3 deep dives and really master these advanced concepts, be sure to head over to forge.college and explore our full range of courses. I'm your host. Thank you so much for hanging out with me today at the Foundry by Forge College, and I'll see you in the next one.